Hey, it's Horner again. We're looking at number 11 through number 20 for the projectile motion in the vector chapter. So this first one says a soccer ball is kicked with the velocity of 25 meters per second at an angle of 45 degrees above the horizontal. So we can go ahead and draw this. Here's our 45 degrees. We've got a soccer ball kicked this way. 25 meters per second. So when we kick it, the ball looks like this, kind of goes up and then comes back down. They want to know what is the vertical component. So remember, vertical is up and down of its acceleration. So we're not talking about speed here. So really, this is just to throw you off. And remember, no matter where the ball is, its acceleration is always downward, 10 meters per second squared. So for this one, your answer should be, or 9.8, 9.8 meters per second squared, and that is downward. Ups, D-O-W-N-W-A-R-D. And that is the answer to number 11. Let's go on to number 12. Number 12 says, if the acceleration vector of an object is directed anti-parallel to the velocity vector. So lots of big words that don't mean much here. If we have something moving in this direction and it has a velocity v, and we take an acceleration vector and make it go in the other direction, we're calling that anti-parallel. So parallel would be if they both pointed in the same direction. So this is velocity and acceleration. This is anti-parallel. If they're anti-parallel, the object, so it doesn't matter what it is, the object will slow down or decelerate. That would happen no matter which way your two vectors are oriented at first. So if this is velocity and this is acceleration, then this thing would slow down on the way up. If we did this, it would slow down on the way down. So this is velocity and acceleration. So if they're opposite each other, just know that that object will be slowing down to you. For number 13, this one says, if the acceleration object is always directed perpendicular to its velocity, then we know that this object is doing something a little bit different. So let's take a look at, let's make a circle. So we're just going to make a really easy circle here. Oh, that's a terrible circle. So let's make a real circle. I think this will be a lot easier. We're just going to make a circle here. And there's our circle. If you remember back when we drew tangent lines are at a 90-degree angle to the surface. So there's one there. Let's make another one here. Let's make another one right here, and let's make another one here. Let's go ahead and make this one red. So if the acceleration of an object is always directed perpendicular to its velocity, so these are all velocities. So this is something going in a circle. Maybe you're looking down at a carousel from the top, or you're watching a roller coaster and there's a car going through it. The acceleration, if it is perpendicular to the velocity, just like this, so these are all accelerations, then we know that this thing is turning. So anytime you have a velocity, okay, so we've got a path, and the velocity is always a tangent line to that path, then we have an acceleration that is at a 90-degree angle. We say that this thing is turning. So that is number 13. For number 14, it says, at what angle should a water gun be aimed in order for the water to land with the greatest horizontal range? So anytime you have a cannon or any other projectile, the best angle to use is 45 degrees. That will give you the most range. Range is just the distance from where the gun shoots to where the bullet or water or whatever it is lands. If I do this at a lesser angle, so let's say that I did it at 25, it's not going to go as far. If I take 90 minus 25, that would give me 65 degrees. And if I did it at a bigger angle, lots of people think it'll go further, but at a bigger angle, well, here, let's make this a little bit better. There we go. So if we made this angle 65 degrees, it's actually going to go a lot higher, but it's going to run out of steam, and it's actually going to land right at the position where the 25-degree projectile was shot. We'll talk about that a little bit more here in a later question. For number 15, it says an Olympic athlete throws a javelin at 4 different angles, each with the same speed. Which 2 throws cause the javelin to land the same distance away? And the rule for this is if you take 90 minus any angle. So let's do 30. The other angle that you end up with, so 9,876, these two angles will have the same range. So the range for 30 and the range for 60, these two things are equal. So if I look, the two that are equal here are going to be 60 and 30. If I take 40 and 30, that's 70. That's still not 90. 60 and 40 is 100. 80 and 30 is 110, so none of that would work. So the two throws would be the 30-degree throw and the 60-degree throw. Both of those would give the same range. Won't have the same path because one's going to go higher than the other. But this is 30. If I launched it at 60, it's going to go up higher, but it's not going to go as far as what you think. So this one is 60 degrees. They both have the same range. For number 16, this one says if you're throwing a ball for you are throwing a ball for the second time. The ball leaves your hand with twice the velocity it had on the first throw. Its horizontal range compared to your first one is going to be different. And for this one, it's actually going to be 4 times as much. So the ball left with twice the velocity. So your velocity here, original velocity would have been, let's say that it's 3 meters per second. If I want to throw it with twice the velocity, so this would be 2 times the original velocity, that would be 6 meters per second. It's actually going to go a lot further. It's going to go 4 times as far. And we will talk a little bit more as to why that is, but for right now, just know that if you double the velocity, you're going to quadruple your range, and there's an equation that goes with that. So we'll do that equation on a different slide. For number 17, it says a ball is thrown at an original speed of 8 meters per second at an angle of 35 degrees. So this is 8 meters per second, and this is 35 degrees. What is the speed of the ball when it returns to the same horizontal level? Well, the nice thing about projectiles in the physics world, not in the real world, but where there's no air resistance, when it takes off at 8 meters per second, when it comes back down, it should also land at the same speed that it was launched at. So notice that this is at the angle of 35. It's also going to land at 35 degrees, and it will have exactly the same speed. So the final answer would be 8 meters per second. Notice it says speed, so we don't really care about this angle, but we do know that that speed that it lands at is 8 meters per second. For number 18, it says when a football in a field goal attempt reaches its maximum height, how does its speed compare to its initial speed? For this one, your speed at the top is only in the x direction. Its speed down here is in the x direction when it's kicked. It's also in the y direction. So we have a Vx and we have a Vy. And if I add these two vectors together, I get this longer arrow. So if this is 5, okay, this speed could be 3, and this could be 4. So notice that its only speed now is 3. Its only speed now is 3. So it is less than, less than, I put 10, the original speed. Okay, so it's less than the original speed that it's launched at. For number 19, this one says a stone is thrown horizontally from the top of a tower. At the same instant, a ball is dropped vertically. Which one is traveling faster when it hits the ground below? So here's our tower, and we're going to have a person standing on the tower. They throw one ball, it comes down, and it hits the ground. And I have another ball that we drop straight down, and they want to know which one of these balls will have which one of these things will have a greater speed. So here is the stone. This is the path of the stone, and a ball is dropped here. Notice that when this stone hits, it has a velocity not just in the y, but also in the x. So it has a y and an x speed. And because the y speed here going down is going to be the same as this length, be careful because we're really looking at the speed at an angle. So the stone will have a much bigger speed than the ball will because it's actually traveling in two directions and this one is only traveling in one direction. So giving it a little bit of oomph in this direction, when it hits the ground, it will hit. Now, the time for fall, so the time for the fall is the same in both cases because they cover the same distance on the way down. So the distance or the height on the way down is the same. So your time to hit is going to be exactly the same because that's determined by dy is equal to 1/2 gt squared. And notice it doesn't accelerate left to right. But they want to know which one's traveling faster, and it is the stone. For number 20, this is the last one in this video, it says a bullet is fired horizontally at the same time a second bullet is dropped from the same height. So we're going to do the same thing again. We're going to fire a bullet. It's going to come down and it's going to hit the ground. We said that the speed of this bullet is going to be faster than the speed of the bullet that's just dropped. But we also just said that the time of fall, so our time to fall for number 1 is going to be equal to the time to fall for number 2. And that's because they both fall the same distance in the y direction. So if we looked at the distance in the y, these two distance in the y's are exactly the same. And according to our equation, this is the only thing that tells us what that projectile falls, how long that projectile falls for. So that is number 20, and that's the end of this video.